IT361 Module 1 Part 2. In this part, we are going to see some of the concepts like paths and connection cycles. A walk in G is a finite non-null sequence W equal to V0 E1, V1 E2, V2 etc. Ek Vk, whose terms are alternately vertices and edges such that for 1 less than or equal to I less than or equal to k, the ends of Ei are Vi minus 1 and Vi. We say that W is a walk from V0 to Vk or a V0 Vk walk. The vertices V0 and Vk are called the origin and terminus of W respectively, and V0, V1 etc. up to Vk minus 1 its internal vertices. The integer k is the length of W. If the edges E1, E2 etc. Ek of a walk W are distinct, then W is called a trail. In this case, the length of W is just E of W. If in addition the vertices V0, V1 etc. up to Vk are distinct, then W is called a path. A walk is closed if it has positive length and its origin and terminus are the same. A closed trail whose origin and internal vertices are distinct is a cycle. These concepts can be made clear with the help of an example. Consider this graph. Here, an example for a walk from this graph is U, A, V, F, Y, F, V, G, Y, H, W, B, V, which is actually an alternating sequence of vertices and edges, where A, F, V, Y, W, A, F, G, H and B are actually the edges, and U, V, Y, V, W are the vertices. So it is an example for a walk. Now trail. From this graph we will get a trail W, C, X, D, Y, H, W, B, Y, G, Y. In this case, the edges are distinct. Say here the edges are C, D, H, B, G. The edges are distinct here. So this walk is a trail. Now if you are considering a path from this graph, it is H, X, C, W, H, Y, E, U, A, V. Here the vertices X, W, Y, U, V are distinct, as well as the edges C, H, E, A are also distinct. Hence, it is an example for a path. Now coming to the concepts of the shortest path problem and Spurner's lemma. First we can see what is a shortest path problem. Before moving to that problem, we just have to familiarize with some of the concepts like weighted graph. With each edge E of G, let there be associated a real number W of E called its weight. Then G together with these weights on its edges is called a weighted graph. If H is a subgraph of a weighted graph, the weight W of H is the sum of the weights sigma E element of E of H W of E on its edges. Many optimization problems amount to finding in a weighted graph a subgraph of a certain type with minimum or maximum weight. One such is the shortest path problem. Given a railway network connecting a various towns, determine a shortest route between two specified towns in the network. Here, one must find in a weighted graph a path of minimum weight connecting two specified vertices U0 and V0. Now coming to the concept of Spurner's lemma. Spurner's lemma concerns the decomposition of a simplex that can be a line segment, a triangle, tetrahedron, and so on into smaller simplices. For the sake of simplicity, we shall deal with the two-dimensional case. First, we can see the concepts relating to simplicial and distinguished triangle. Let T be a closed triangle in the plane. A subdivision of T into a finite number of smaller triangles is said to be simplicial if any two intersecting triangles have either a vertex or a wall side in common. We call a triangle in the subdivision whose vertices receive all three labels like 0, 1 and 2 as a distinguished triangle. Now the Spurner's lemma states that every properly labeled simplicial subdivision of a triangle has an odd number of distinguished triangles. Now we are going to prove this lemma. For that, let T0 denote the region outside T, and you know that T is a closed triangle in the plane, and let T1, T2, etc. Tn be the triangles of the subdivision. Construct a graph, and we know that these T1, T2, etc. Tn are actually the triangles which are simplicial in nature. Construct a graph on the vertex set V0, V1, etc. Vn. By joining Va and Vj whenever the common boundary of Ta and Tj is an edge with the labels 0 and 1. So that's the logic behind that's the connection between the vertices and the corresponding Ta and Tj. So according to so this is the figure relating to the triangle, the region T and the T0 and the other regions, say T1, T2, T3. Each of these regions, T1, T2, T3, all these things are actually simplicial triangles. So how this regions and the vertices are connected, that is told over here. Whenever the common boundary of Ta and Tj is an edge with the labels 0 and 1, then the corresponding Va and Vj vertices will be joined. As you can see, if you are observing T0 and T2, T0 is the outer region and T2 is the is one of the region inside the triangle. And you can see there exists an edge 0 and 1 which is common to T0 and T2. Hence, the V0 and V2 can be joined. Similarly, the T0, if you are considering T0, the regions T0 and T5, there exists an edge 0, 1 which is common, which is a common boundary of T0 and T5. Hence, the corresponding vertices V0 and V5 are joined with the help of an edge. But if you are considering V2 and V3, the corresponding regions are T0 and T3, and you can see that there exists no region or no common boundary for them. Hence, the corresponding vertices V0 and V3 are not at all joined with an edge. So that's the logic behind the edges that exist between VAs and VJs and the corresponding to the regions, say TAs. In this graph, if you are observing V0, you can see the degree of V0 is 3 and 3 is an odd number. Hence, we can say that V0 is clearly of odd degree. Since in a graph, the number of vertices of odd degree is even, it follows that an odd number of the vertices V1, V2, etc. in the remaining vertices V1, V2, etc. Vn are of odd degree. Because in a graph, the number of odd degree vertices is even. Since we got one of the vertex, say V0 is already of odd degree, that means then there exists an odd number of vertices, because together along with V0 it should form even. So the remaining vertices of odd degree will be an odd number. Now it is easily seen that none of these vertices can have degree 3. If you are observing the graph, you can see only V0 has got the degree 3 and the other vertices are not at all, there exists no other vertex in the graph which is of degree 3. So and those with the odd degree, remaining vertices, in the remaining vertices, those with the odd degree must have degree only 1. So if you are observing in the vertex set, you can see in the remaining vertices, the odd degree vertices are only those vertices having degree 1. But a vertex VA is of degree 1 if and only if the triangle TA is distinguished. That is clear from the diagram itself. Just see the figure here. Here you can see V2 is of degree 1 and V2 actually corresponds to the region T2. And if you are observing that T2, the triangle corresponding to T2 is a distinguished triangle because it consists of all the three labels, say it comprises of the all three labels, say 0, 1 and 2. So that means here we have reached the concept that the number of odd degree vertices should be odd, and we have seen that the remaining vertices are of odd degree 1. The odd degree vertices are of degree 1, and since degree 1 corresponds to a distinguished triangle, and it concludes that the number of distinguished triangles is odd here. So hence there exist odd number of distinguished triangles. Moving to the concepts trees, cut edges and bonds. For subsets S and S dash of V, we denote by SS dash the set of edges with one end in S and the other in S dash. An edge cut of A is a subset of E of the form SS bar, where S is a non-empty proper subset of V and S bar equal to V minus S. It's not an edge cut of A, it is actually an edge cut of G is a subset of E of the form SS bar, where S is a non-empty proper subset of V and S bar equal to V minus S. As you can see in the diagram, the dark lines shows the edge cut of the given graph G. A minimal non-empty edge cut of G is called a graph, is called a bond. In the diagram given below, the dark lines actually indicates a bond. A graph G is said to be connected if there is at least one path between every pair of vertices. Otherwise, it is a disconnected graph. A tree is a connected acyclic graph. The graphs given below are some examples of trees with 6 vertices. In all these trees, you can see all the trees are connected and there exists no cycle in each of the trees. Hence, a connected acyclic graph is called a tree. A cut edge of G is an edge E such that omega of G minus E greater than omega of G, where omega of G denotes the number of components of G. So, an edge will become a cut edge if the number of components in omega of G minus E is greater than the number of components in G. In the graph given below, you can see if you are excluding any one of the edge from the given graph, the number of components will increases by 1. If you are removing the last edge given, which is given in a dark line, then the number of before removing that, the number of components in the graph is 1. But by removing one of the darker lines here, you will get the number of components of G minus that edge equal to 2. So such type of edges are called cut edges, and in the given graph there exist three cut edges which are shown by the dark line segments. Now, based on this concept of trees and cut edges, we can prove a theorem. A connected graph is a tree if and only if every edge is a cut edge. First, we can prove, suppose that a connected graph is a tree. We have to prove that every edge in that tree is a cut edge. So, let G be a tree and let E be an edge of G. Since G is a tree, it will be connected and acyclic. So, since G is acyclic, E is contained in no cycle of G and is therefore a cut edge of G. Because if E is not contained in any cycle of G, the removal of E from the graph G will result in increase the number of components of G minus E by 1. Hence, that edge E forms a cut edge of G. Now, conversely, we will suppose that G is connected, but G is not a tree. Then if G is connected and it is not a tree, means G will contains a cycle. If G contains a cycle, then no edge of C can be a cut edge of G. Hence the theorem. Now these are some problems from this topic. Try to do it by yourself. So that's all from this part. Thank you.